I, Abhishek Misal from UTD CSUT Bhilai, welcome you to this lecture on amplitude shift keying and frequency shift keying from the course of Fundamental of Communication System and its application. In the previous lecture, we study the binary coding, data transmission, pulse code modulation. In the previous lecture, we study the different binary coding technique like binary coding, ASCII coding, checksum coding, etc. Then we study the pulse code modulation and their block diagram, the different advanced technique of pulse code modulation like adaptive pulse code modulation and their application. In digital communication, data is transmitted from one place to another using various modulation techniques. These techniques encode the digital information into an analog carrier signal, making it suitable for transmission over different communication channels. Among these modulation techniques, amplitude shift keying, that is ASK, and frequency shift keying, that is FSK, are two of the simplest and most common method used. They play a crucial role in many communication systems, including telecommunication, wireless communication, and data transfer over various media. This lecture will explore the principle, working and application of ASK and FSK in detail. Here we study first amplitude shift keying, that is called ASK modulation. Amplitude shift keying is a simple and elementary form of basic digital modulation technique where the amplitude of carrier wave is vary in accordance with the digital signal. The carrier wave is typically a sinusoidal waveform and the amplitude changes discretely based on the modulating symbol. For a given group of m bit that from one symbol, one can design m is equal to 2 to the power m. Different baseband signal DMT within the interval of 0 less than equal to t less than equal to capital T. When a symbol modulates the carrier Ct is equal to cos omega Ct. The resulting modulated signal is Sm in the bracket T is equal to dmt into cos omega Ct. This technique is classified as narrowband modulation with the assumption that the carrier completes a large number of cycles within one symbol interval, that is t upon 2 pi omega c is a large integer. It is obvious that the information is embedded only in the peak amplitude of modulated signal. So, this is a kind of digital amplitude modulation technique from another signal. One can describe this scheme of modulation as one-dimensional modulation scheme where one basic function, that is phi t is equal to root over 2 by t cos omega underscore c t defined over 0 less than equal to t less than equal to capital T and having unit energy is used and all the baseband signal are linearly dependent. In ASK, the information is embedded solely in the peak amplitude of the modulated signal, making it is a type of digital amplitude modulation. Now, amplitude phase shift keying is widely used in communication system, practically in satellite communication due to its ability to provide high data rate and spectral efficiency. Now, let us discuss the block diagram. The block diagram shown in here, the block diagram of FPSK modulator can be divided into several key components. The first component is input data stream. The input data stream is a sequence of binary digits that represent the information to be transmitted. This stream is first processed and grouped into a symbol. Each symbol can represent multiple bits depending on the modulation order of APSK. Mapping and symbol generation. The binary input data is mapped to a specific symbol in the APSK diagram. APSK typically use circular constellation where points are arranged in multiple concentric circles. The mapping process associated each binary sequence with a particular amplitude and phase, which correspond to a unique point in the consultation. Amplitude modulator. The amplitude modulator adjusts the amplitude of the carrier signal based on the map symbol. Since APSK combine amplitude and phase modulation, this step is crucial to ensure that each symbol has the correct amplitude as defined in the consultation diagram. Phase modulator. The phase modulator adjusts the phase of carrier according to the map symbol. The phase shift is determined by the angle the symbol in the consultation diagram. Carrier signal generator. The carrier signal is a high frequency sinusoidal waveform that serves as a base signal for modulation. The amplitude and phase modulator modify this carrier signal to encode the input data. Now we discuss the summation and modulation output. The modulated output signal is generated by combining the amplitude modulated and phase modulated carrier signal. This composite signal is then transmitted over the communication channel. Now next is power amplifier, which is optional block diagram. You can put or you can remove. It is depend on the requirement. In some system, the modulated signal is passed through a power amplifier before transmission. This step ensures that the signal has sufficient power to be transmitted over long distance without significant degradation. Waveform of APSK. The waveform of APSK is a combination of amplitude modulated and phase modulated signal. Depending on the number of amplitude and phase level, the waveform can vary significantly. Let's break down the waveform characteristic. The first is amplitude level. In the APSK, the carrier signal's amplitude can take on different discrete level. The number of amplitude level depend on the modulation scheme. For example, in 16-bit APSK, there could be a multiple amplitude level distributed across the consultation point. Phase level. The phase of carrier signal is shifted according to the symbol phase angle in the consultation diagram. This phase shift occur at each symbol transition depending on the order of APSK. There could be a multiple discrete phase signal. Now let's discuss the consultation diagram. The consultation diagram for APSK is a circular with point arranged in concentric circle. Each point represents a unique combination of amplitude and phase. The distance between points on the same circle is determined by the phase shift, while the distance circles is determined by the amplitude difference. Now, let's discuss the time domain representation. In the time domain, the waveform of an APSK signal show change in amplitude and phase at symbol boundaries. The signal amplitude might vary in discrete step and the phase will shift according to the map symbol. The next representation is frequency domain representation. In the frequency domain, APSK signal occupy a certain bandwidth. The spectral efficiency of APSK is higher than traditional ASK or PASK due to the combined use of amplitude and phase modulation. The spectral content show peak the carrier frequency and sideband resulting for the modulation process. Detailed explanation of the block diagram and waveform of the APSK is here. We use the input data stream. The input data stream of binary information that need to be transmitted. From example, consider a 16-bit APSK system where each symbol represent a 4-bit data. If the input data stream is 11001001, it would be divided into two symbols, that is 1100 and another is 1001. Here let's discuss the mapping and symbol generation. Each of the 4-bit sequence, that is 1100 and 1001, is mapped to a symbol in the APSK. Consultation. In the 16-bit APSK, the consultation might have 12 points arranged in a circle and 4 points in the inner circle. Each point represents a specific amplitude and phase. And now go on to the amplitude modulator. For the symbol corresponding to 1100, suppose it is mapped to a point on the other circle. The amplitude modulator adjusts the carrier's amplitude to match this point amplitude. If the next symbol 1001 is on the inner circle, the amplitude modulator reduces the carrier's amplitude accordingly. The next is phase modulator. The phase modulator shifts the carrier phase based on the angle of the map symbol in the consultation diagram. For 1100, the phase might be shifted by 45 degree, and while 100 it could be shifted 135 degree. This shift correspond to the angular position of the point in the consultation. Now let's discuss the carrier signal generator. The carrier signal is continuous sinusoidal waveform at a specific frequency. The amplitude and phase modulated signal will be superimposed onto this carrier to produce the final modulated signal. Now let's discuss summation and modulated output. The amplitude and phase modulated signal are combined to produce the final output signal. The resulting waveform will show variation in both amplitude, and phase corresponding to the input data. Once again, we discuss the power amplifier. In the system long distance transmission, the modulated signal might be passed through a power amplifier. The amplifier boosts the signal's power, ensuring it can travel over the communication channel with minimum attenuation. Let's discuss the waveform characteristic. In the time domain, the APSK signal will show discrete jump in amplitude and abrupt shift in the phase at each symbol transmission. These changes correspond to the different point in the APSK consultation. For instance, if the signal is transmission from 110 to 1001, the amplitude might drop, it move the outer of the inner circle, and the phase might shift by 90 degrees. The waveform will reflect these changes. Now, let's discuss the consultation and signal quality. The consultation diagram is a key tool in analyzing APSK signal. It helps visualize how well the signal is modulated and transmitted in an ideal scenario. All received symbol should be closely match the original consultation point. However, due to noise and other facts, the points might deviate, leading to the error. The error rate in APSK can be mitigated by choosing an appropriate modulation order and implementing error correction techniques. Spectral efficiency. APSK is known for its high spectral efficiency, especially in higher order modulation scheme. By combining amplitude and phase modulation, APSK can transmit more per bit symbol, leading to the better utilization of the available bandwidth. The efficiency makes APSK particularly attractive for the application like satellite communication, where the bandwidth is limited resources. The application and advantage of APSK. APSK is widely used in scenario where high data rate and efficient bandwidth utilization are crucial. Some key application includes satellite communication. APSK is extremely used in satellite communication system, particularly in the DVB-S2 standard, which is widely adopted for broadcasting and data transmission over satellite. The high spectral efficiency of APSK make it ideal for this application. The next application is wireless communication. APSK can be used in wireless communication system that require high data rate and efficient bandwidth uses. It is particularly useful in scenario where power efficiency also a concern, as APSK can be adopted to balance spectral and power efficiency. The next is high speed data transmission in system. Requiring high speed data transmission, APSK can provide the necessary data rate while maintaining robustness against noise and other impairment. High spectral efficiency. APSK ability to transmit more bit per symbol compared to traditional modulation scheme. Adaptability. APSK modulation scheme can be adjusted to balance between spectral efficiency and power efficiency, making it versatile for various applications. The next is robustness with appropriate error correction technique. APSK achieve lower error rate even in challenging transmission environment. Challenges and consideration in APSK. Now we discuss the difficulty or disadvantage, but here we use more positive word, that is challenges and consideration of APSK. While APSK offer many advantages, there are also challenges to consider. First, complexity. The combination of amplitude and phase modulation increase the complexity of both the modulator and demodulator. This complexity can lead to high power consumption and cost is implementation, signal distortion, nonlinear in the transmission channel, particularly in power amplitude, can distort APSK signal, leading to higher error rate. Careful design of the transmission system is required to mitigate this effect. Now, the error correction. Due to the complex nature of APSK signal, effective error correction techniques are necessary to ensure reliable communication, particularly in noisy environment. The next topic is on-off keying, that is OOK. On-off keying is a straightforward form of amplitude shift keying used to encode binary data. Use binary data by toggling the presence or absence of the sinusoidal carrier. For instance, during a bit duration TB, the presence of the carrier can represent a binary 1, while the absence can signify a binary 0. This method has historically been employed moreover specific radio frequency or for telegraph communication. However, on-off keying is not particularly efficient regarding spectral usage because the carrier amplitude shift abrupt with each changes in data bit. Therefore, while on-off keying is suitable for transmission data at low to moderate rate, more bandwidth efficient phase modulation techniques are preferred to higher data rate. Now, let us discuss the frequency shift keying. Frequency shift keying is another popular digital modulation technique often used in low-cost application for transmitting data at moderate or low rates over both wired and wireless channel. In the FSK, different frequencies are used to represent the symbol. Specifically, in binary frequency shift keying BFSK, two distinct carrier frequencies are employed. One frequency, the mark frequency F2, represent a binary 1, while the other frequency, the space frequency F1, represent a binary 0. The time limited signal for BFSK can be expressed as T is equal to root over 2 EB upon TB cos 2 pi FT, which is 0 less than equal to T less than equal to dB for 1. In certain case, the two frequency F1, F2 can be chosen to be orthogonal over bit duration TB. F1 is equal to M TB and F2 is equal to N TB, where M and N are positive integer with N M the spectration the separation with n less than equal to m, the separation between two frequency is del f is then given by del f in the bracket n minus m rb, where rb is equal to 1 and tb is the bit rate. Now, binary frequency shift keying modulation can be implemented using a simple scheme where the binary input sequence select between two oscillator of frequency f1, f2. However, in practice, using two independent oscillator can cause issue with maintaining orthogonality due to the phase shift. A more reliable approach is to use a voltage controlled oscillator that is driven by the modulated signal. Frequency shift keying modulation. Frequency shift keying modulation is the one of the simplest form of digital modulation technique. FSK is form of continuous phase frequency modulation where binary 1 or 0 is represented by different frequency. It is simplest form known as binary FSK. Two distinct carrier frequency are used. However, more complex form like multi-frequency shift keying use multiple frequency to be represent more than one bit at a same time. Here we discuss the block diagram of FSK modulation. The block diagram of FSK modulator includes several key components that work together to produce modulation signal. Let's break down the each component. First is input data stream. The input data stream consists of binary digit that represent the information to be transmitted. This stream can either be data or a specific bit pattern depending on the application. Now, let's discuss the frequency generator. The frequency generator produce the two or more frequency required to FSK modulation. In BFSK, only two frequency are needed. One frequency is F1 and which is represent 1 and another frequency is F0 for binary 0. In MFSK, multiple frequency are generated. Data encoder. The data encoder convert the binary input data into a form that can be used control the frequency generator for BFSK. The encoder produce a control signal that switches between the two frequency based on whether the input bit is 1 or 0. For MFSK, the encoder generates a signal that select one of the multiple frequency. Now, the frequency selector often implement as a multiplexer chosen the appropriate frequency generated by frequency generator based on the control signal from the data encoder. The selected frequency correspond to the binary data being transmitted at any given moment. The next is carrier oscillator. The carrier oscillator generates a continuous sinusoidal signal at base frequency. The next is modulated output signal. The output of FSK modulated signal whose frequency vary accordance with the input data. For binary 1, the signal will have a frequency f1 and for binary 0, the signal is 0. It will have the frequency f. The next is power amplifier. Similarly, other modulation scheme, the power amplifier might be used to boost the modulated signal before the transmission, ensuring it can travel longer distance without significant attenuation. The next is transmitter. Finally, the modulated signal is transmitted through a communication channel, which could be a wire medium, radio wave, or optical fiber, depending on the system design. Waveform of FSK modulated signal is characterized by changes in frequency over time. The key feature of the waveform is frequency shift. The most distinctive feature of FSK waveform is shift between different frequency representing binary data. The next is continuous phase. In continuous phase frequency shifting, that is called CPSK, is the phase of carrier signal remains continuous even during frequency shift. This is important for minimize the signal. The next is time domain represent. In the time domain, the FSK signal appear as a sinusoidal waveform that oscillate at different frequency depend on binary input. The transmission between frequency are smooth in CPFSK, where in simple FSK the transmission can be more abrupt. The next is frequency domain represent. In the frequency domain, the FSK signal is represent two or more distinct frequency. For example, in the BFSK, these components are two discrete peaks of F1 and F0. In MFSK are multiple peaks. Let's discuss the application of FSK is in radio communication. It is used to transmit the data in radio communication. The next is telegraphy, coherent and non-coherent demodulation. From this, we conclude our lecture. In this lecture, you study the ASK and their modulation technique, and the next is FSK, where the frequency modulation is given. I hope you enjoy this lecture and learn much more. Thank you very much for your patience listening.